So in the last segment, we considered the data structure called heaps or priority queues. One thing I did not mention in that segment, and something you might think about, is that heaps can actually be used to sort. To sort an array of n numbers, what you do is make a heap out of those n numbers by inserting each one maybe into the heap, to an initially empty heap. And then how would you get the sorted array? Just repeatedly extract the minimum from the heap, and what you get is the elements in increasing order. So this is called heap sort, and heap sort is a very good sorting algorithm, as good as merge sort and quick sort. You can try to analyze this for yourself. But this time you're going to move on to a different data structure, a very important one that's used all over the place. The data structure has an odd name, but it belies the fact that it's crucial to so many applications. It's called a dynamic dictionary. So what's a dynamic dictionary? You all know what a dictionary is. Maybe some of you do. Maybe some of you are too young to know a real dictionary. But a dictionary is basically a book which contains all the words in some language and their definitions and other things about those words. And luckily for us, a dictionary is arranged so that the words are in alphabetical order. So you can think of it as a sorted array of elements. And so when you're looking for a word in a dictionary, so what do you want to do with a dictionary? I mean, the main thing you do with a dictionary is to find words in it. So it's basically the find operation, which is you have a certain word in mind, you go open the dictionary and find your way to that word and look up its definition. That's the find operation. What makes a dictionary dynamic is the ability for you to add words to the dictionary or remove words from the dictionary besides finding words. So if you have a dictionary that you create for your own crazy language and you want to invent words today and you add them to the dictionary, you can do so. That's the inserting words into the dictionary. And you may not like a word at some point. You may decide you don't want it in your language anymore, and you can just delete it. So if you can do all of those things, you have a dynamic dictionary. And such dynamic dictionaries are very important in a number of applications. One such application might be databases. One simple way of thinking about databases is it's just a collection of records where each record has a key. Think of a company that has a payroll of all of its employees. It's a standard example of a database. So then you have a record for each employee, and you may organize them by their ID number or some other kind of key that uniquely identifies each employee. And employees may come in, employees may leave the company, so you want to be able to insert records for new employees. You want to be able to delete records of employees who've left. And sometimes you want to be able to find an employee's record to make changes to it perhaps, or to look up some information in it and so on. So you can see that's one example of a dynamic dictionary use. Other examples come up in networks, in routing, routing internet traffic, and so on. So let's again talk about the abstract representation of a dynamic dictionary, and then talk about how we might implement it later on, just as we did for priority queues. So abstractly, a dynamic dictionary is maintaining a set of records, if you like. I'm using that term rather loosely. A record has a key. In this case, there are two records, the record with key 2 here and the record with key 1 here. So those are the two records in the dictionary. The record with key 1 is here. And each record has some other information associated with it, as you can see here. In this case, each key has associated a value, which is a word. That's not so important. So now we might want to insert the pair, a new record, which consists of the key 3 and the value the. And you just, then the bag of word, the set of elements in the dynamic dictionary now has 3 elements in it. So you may want to now look up one. So that's look up or find or search. These are all words for the same thing. So you look up one, and what that should return is the record with 1 and the word hi associated with it. So next you may want to delete 3 from the dictionary, and then the bag will now contain just two records with 1 and 2, with the keys 1 and 2. So that's the basic operation of a dynamic dictionary in abstract terms. Now, how do we implement such a data structure efficiently? Well, let's try a few options. One is to try to implement the dictionary as an array. So what you do then is you keep all the records in the dictionary in an array in the form shown here. So it's like an array of records where there's one record for each key. Now, if you want to look for a particular record in this array, if you don't keep the array sorted by key or anything like that, your only option is to search through the entire array, and that can take order n time, where n is the number of records in the array. Similarly, insertion and deletion can also take order n time, because if you're looking if you're looking to delete an element with a key I, you have to go find the element with key I first, which may be anywhere in the array, and that takes order n time. Insertion could potentially be done in order 1 time if you're willing to insert everything at the beginning of the array, at the end of the array, I mean. But if you want to maintain order, then the insertion can also take order n time. And so, yeah, insertion and deletion may involve resizing the array as well. That could also cost order n time. Let's look at another option, which is using linked lists. So you all know what linked lists are. You can try to search, insert, and delete in a linked list. But again, unless you maintain the keys in some suitable order, searching or inserting or deleting can take order n time, because you don't know where you're going to find that element or where you're going to put that element. Now, in order to maintain a linked list or an array in the right order, you still have to move things around. If you're going to maintain an array in order, if now you get an element, a record with the smallest possible key, you have to shift all the other elements in order to fit this in. So that's going to take order n time too. So maintaining an array in order is not the answer, because order n is a bit too high. We want to do much better than that. And linked lists also are problematic, because there is no random access in a linked list. The only way to access an arbitrary element in a linked list is to start at the beginning and walk your way to the right element, unless it's a doubly linked list where you could start at the end as well. But in any case, there is no random access in a linked list. So neither of these are great ideas. We want to try to do much better than order n, as I said. We will use an idea that looks like divide and conquer. Incidentally, I want to back up and say that the priority queue is kind of a divide and conquer solution as well, because you never have to search the entire set. You have to, for any operation you do, you're always choosing 1/2 to search through. So that's, and binary search trees are much more clearly a divide and conquer kind of solution. So what we're going to do is maintain a dynamic dictionary as a binary search tree. So what is a binary search tree? It's a rooted binary tree, just as a priority queue, but it has slightly different properties from a priority queue. So what it's going to have is that the keys are going to have a certain order property that's different from a priority queue. The key at any node is going to be less than the key at any node in the left subtree, and greater than the keys at any node in the right subtree. Supposing we have a binary search tree which has one node with key 4 and value A, and we want to insert the record 2, B. Well, the key 2 is less than the key 4, so we should put it in the left subtree of the root. So we put it there. Now this still satisfies the binary search tree property, because the key at the left node, at the left child 2 is less than the key at the root 4. And we can, if you want to insert the key in the record 7C, because 7 is greater than 4, one place we can put it is to the right of 4, and so on. So we can build a binary search tree like this. So, and then if you want to search for the element 3, this is where the divide and conquer aspect of binary search trees becomes clear. When you're looking for the element 3, we compare it to the root key, and we see that 3 is less than 4. So then what we can do is, we know that if 3 occurs in this binary search tree, it must occur only on the left side of 4, because of the binary search tree property. So we can divide the problem and only solve the sub-problem on the left side, ignore the right side completely. So we go down from the root to the left subtree, to the node with key 2. Now we see that the key we are looking for, 3, is bigger than the key at this node, which is 2. and we know we need to look to the right, and when we look to the right, we find our key. So the time to insert, search, and delete in a binary search tree is proportional again to the height of the tree, because each of these operations involves starting at the root and taking a path down towards the leaf. How bad can the height of a binary search tree be? Well, in the worst case, if you get a sequence of insertions that are elements in order, like insert 1, A, you put it there, 2, B has to be a right child. And if you don't change what root we have, and we keep on going like this, we don't change what we've built already, then you're going to build up a tree that looks like a long path, as shown here. So now if you're looking for the element 5, what you're going to find is that you have to take a path that's as long as the number of elements in the tree, which is 5, or 1 less. But essentially, the height of the tree is going to be close to the number of elements in the tree if you're unlucky. But the common case, it's not so bad. The common case is that again, it's a binary tree, and if there's lots of nodes at each level, you expect the height to be about order log n. And in fact, there's a couple of things we can do. To ensure the common case is really the correct case. How can we get the worst case height to be order log n? Well, there are ways of balancing a binary search tree that we won't talk about in this course, where every time you insert, delete, or search for an element in the tree, you do a little bit of bookkeeping to prevent the tree from getting very lopsided. If you keep doing that consistently all the time, you can ensure that the height of the tree is order log n, and then all of these operations would be worst case order log n.